Hey everyone, in today's video we're going to be discussing part 1 of molecular geometry and molecular polarity. These are two very important concepts when discussing full molecules, as it discusses these molecules in 3D as opposed to simply a 2D Lewis structure. So when we talk about molecular geometry, we also have to talk about something called electron group geometry. So the best way to do this is through examples. So here in this chart I have molecules here, what the Lewis structure of those molecules should be, what the electron domain geometry should be, the molecular geometry, and if the molecule is polar or nonpolar. There's an easy way to tell if a molecule is polar or nonpolar, and we'll be covering all of that in this video. So let's start with carbon dioxide. So we have to first draw the Lewis structure to be able to find out any of this. So to draw our Lewis structure, we know carbon has 4 valence electrons, oxygen has 6, times 2 is 12, 12 plus 4 is 16. So we need to include 16 here. So we have C, O, and O. We're going to link these together, complete our octets. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. This is pretty easy. We can just cross off a lone pair from each atom and then the central atom, and then we're left with this. So this is our Lewis structure. This will have 16 since we crossed off our four different lone pairs, so that will reduce our total electron count by 4 to give us from 20 to 16. So when we talk about electron domain or electron group geometry, we have to see how many groups of electrons in either lone pairs or atoms are around the central atom. Again, the best way to illustrate this is in 3 dimensions. So if you look at this looks like a line, right? So if we have our central atom, which I'll represent all of these molecules with this large green styrofoam ball, if I have my central atom and then around it I have 2 places where electrons might be found, then that means in 3 dimensions, regardless of if this represents a lone pair or actual atoms, then it's going to form a linear structure. Now when discussing carbon dioxide, there are obviously 2 oxygen atoms surrounding the central carbon atom. So we're going to be left with this sort of linear geometry. Now, to answer these questions, our electron group or electron domain geometry would be linear, because regardless of if the electrons are found as atoms or lone pairs, there are still 2 bonding groups or non-bonding groups. It doesn't matter when talking about electron domain geometry around the central atom, so that will give us linear. Our molecular geometry depends on the atoms, not only the lone pairs. It matters if the groups of electrons around the atoms are lone pairs or atoms like this. So this will also be linear because obviously it looks like a line, and there are 2 atoms, there are 2 bonding groups around our central atom. So that's how we would answer this question. Now, is the molecule polar or not? So when discussing this, when discussing the polarity of an entire molecule, we have to look exclusively at its molecular geometry, and also as the lone pairs, or lack thereof in this case, on the central atom. So we know that the carbon-oxygen bond is a polar bond, but if oxygen is more electronegative here and oxygen is more electronegative here, they'll be pulling in equal and opposite forces, meaning that those polar bonds will actually cancel out. This means that the molecule carbon dioxide has what's called a dipole moment of 0. Dipole moment is the overall dipole attraction of the entire molecule. So it's nonpolar because these 2 oxygens each pull electrons in equal and opposite forces, so that will give us nonpolar. There is no net pull in our shared bonds. So let's look at a different molecule, CH2O formaldehyde. So when drawing our Lewis structure for this, we are going to use carbon as our central atom, and then we're going to put H, H, and O. Let's count 4 times 2, 1 times 2, that's 6 right there, then plus 6, we need 12. So if we then add our lone pair, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So because hydrogen cannot have a double bond, we're going to have to replace these lone pairs with a double bond right here, and this will give us 12 electrons. So let's look at the electron domain geometry of formaldehyde. So there are 3 different groups around our central atom, and there are 3 atoms around our central atom. But the fact that there are 3 atoms would help us solve this question, not this. So if I were to look at this molecule in 3D space, it would look like this. So there's an important phenomenon in chemistry called VSEPR theory, valence shell electron repulsion, meaning that electrons, obviously because they're negatively charged, will tend to repel each other. So we want to have the farthest space in between 2 electron bonding groups possible in 3-dimensional space. So this orientation will give it to us. This sort of looks like a triangle, right? 1, 2, 3 vertices, and we can make through 3-sided shape. So this electron domain geometry is called trigonal planar. The second word, planar, is important because we have to see that all the atoms are in the same plane. As you might remember from your normal mathematics geometry courses, a plane can cut through in 2-dimensional shapes. If I ran a plane right through the center of this atom, it would include parts of all of these outer atoms, which gives the name trigonal planar. The molecular geometry would be the same because we have no lone pairs on this central carbon, and we only have lone pairs on this oxygen, which won't affect the molecular geometry. The molecular geometry of formaldehyde will also be trigonal planar. And I should be representing this with a double bond, but it won't actually matter when determining the electron domain geometry and the molecular geometry. So is this molecule polar? We talked about before how in carbon dioxide the poles will cancel out to give a dipole moment of 0, but these are not the same bonds. Hydrogen-carbon bonds do not have the same electronegativity difference as oxygen-carbon bonds, meaning that if we said this was our oxygen, it would have a much stronger dipole than any of these 2 bonds. So there would be a net dipole moment. The dipole moment would not be 0, so that means our molecule must be polar. So let's move on to sulfur dioxide. So let's first draw our Lewis structure. So sulfur dioxide, for oxygen, I'll start here. It has 6 times 2 will give us 12 valence electrons. Then sulfur will have 6, as we should remember from our periodic table. So that will give us 18 valence electrons. So that's 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So this molecule actually will exhibit resonance, but it won't affect our electron domain geometry or our molecular geometry. So we counted that we need 18, but we counted 20 here. So that means we can either make this a double bond and cancel this and remove this lone pair, or we can do the same on the other side. So in this case, when we look at our electron domain geometry, we'll see that there are again 3 bonding groups around the central atom. 1, 2, regardless of if we have the double bond on this side or this side, and 3. 1, 2, 3 bonding groups around. So this is what I mean when it doesn't matter when looking at electron domain geometry if it's an electron in terms of lone pairs or atoms. This geometry will actually still be trigonal planar, except we remove this and I'll let this toothpick represent this lone pair on our central sulfur atom. So, but however, even though we'll have a trigonal planar electron domain geometry because we have 3 groups around our central atom, this does not mean that our molecular geometry will also be trigonal planar. Trigonal planar. Did not finish writing that. So, because of valence shell electron repulsion theory, VSEPR theory, this lone pair will actually push these down. So this will result in a molecule whose molecular geometry is known as bent. I'll put bent number 1 for reasons that we'll see a little bit later on when we talk about water. So this molecular geometry is bent, and this electron domain geometry is still trigonal planar. So, is sulfur dioxide polar? The answer is yes, it is, for reasons that we explained above. The lone pair combined with these two oxygens, even though they're the same oxygen, they're the same type of atom, won't cancel out, so there will be a net dipole moment. So now let's look at methane. Methane has one of the easiest to draw Lewis structures out of many different organic molecules. So we'll see that we have 4 plus 4 will give us 8. 1, 2, 3, 4, 5, 6, 7, 8. That was easy. So when we look at our electron domain geometry, we'll see that there are actually 4 different groups around our central carbon atom. So we won't have the same trigonal planar. In fact, the trigonal planar electron geometry, because tri means 3. Now if we think about other chemistry namings, you might hear about like tetroxide. Tetra means 4. So the electron domain will actually be tetrahedral. And this is what they would look like in 3-dimensional space. So we would see this, we would see something that would look like a bent, but we would add on the other side another atom, or it could be another lone pair, and then on top we would have this. So it looks like a bit of a tetrahedral shape. So even though, I'm sorry, this is not equal, this is not even, this is what it would look like in 3-dimensional space. It would not be flat, square planar, which is a type of molecular geometry we'll get into the next video, but it would rather look like a tetrahedron. This atom would be physically behind this. They would not be in the same plane. They would not be coplanar. So then molecular geometry will be the same. When there are all atoms and no lone pairs, the electron domain geometry and the molecular geometry will be the same. So even though you may expect that this molecule would be polar, it's actually nonpolar, because all of the surrounding hydrogen atoms around the carbon atoms, all of these bonds will actually cancel out in 3-dimensional space, so methane will have a dipole moment of 0, meaning that this molecule is in fact nonpolar. We only have 2 more to go. So now NH3 is a molecule that's commonly known as ammonia. So when we draw this Lewis structure, we'll look at the 5 valence electrons of nitrogen plus 3 times 1. This will give us 8. So we have N, H, 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 connect them, and then we're done. 1, 2, 3, 4, 5, 6, 7, 8. Pretty easy Lewis structures here. So at the electron domain geometry, we'll see that there are 1, 2, 3, 4 groups around the central nitrogen atom. So that means that our electron domain geometry will also be tetrahedral, because it doesn't matter if those electron groups are lone pairs or atoms. But if we look at the molecular geometry, we'll have to remove this outer atom. So this would be replaced with the atom would be replaced with a lone pair, as represented by this toothpick here, and this would give us something called pyramidal geometry. Pyramidal. Again, according to Vesper theory, this lone pair here would push these atoms much farther down, so it would look like a pyramid, hence the pyramidal name. See, if I put it here and if I put it equally, it would stand like a pyramid. So is this molecule polar or nonpolar? It will be polar, because the dipoles would not cancel out between the 3 surrounding hydrogens and the upper lone pair. So the answer is ammonia is polar. As a general rule, with all types of molecular geometry, well, actually most types of simple molecular geometry, the more complex ones that I'll get into the next video, this isn't always true. If there is a lone pair on the central atom here, chances are it's going to be a polar molecule, because it won't be able to cancel out any of these other dipoles. So we have one of the most common molecules that you'll deal with in chemistry, H2O, water. So oxygen will have 6 valence electrons, plus the 2 will give us 8. So we have O and H, link them together. Then 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8. So 8 and 8, this is the correct structure. So Now we see that we have two lone pairs here on our central oxygen atom. So I would have to remove this. So even though we have two lone pairs here, we still have 4 electron groups around our central oxygen atom. This hydrogen, lone pair 1, lone pair 2, and lone pair 1, 2, and then our second hydrogen. So that means our electron domain geometry would still be tetrahedral because we have 4 different bonding or non-bonding groups around our central atom. But notice how once we remove these the outer hydrogen atoms, once we remove other outer atoms that don't necessarily have to be hydrogen, I'm going to cut this part out, is we're left with a bent geometry, but it's not the same. The electron domain geometry here would be trigonal planar because there are 3 groups around and only 1 lone pair on the central atom. Here there are 2 lone pairs, but it still represents that same bent shape. This bond angle will be different. Most of the times you don't have to memorize bond angles for any chemistry courses, but it's important to recognize that these bond angles will be in fact different. So this gives us bent number 2. There are 2 types of bent in chemistry, one in which there are 2 lone pairs in the central atom, like in water, and one in which there's 1, like sulfur dioxide. So is this molecule polar? The answer is yes, it is. Because, as for the same reason as in ammonia, the lone pairs will not cancel out, the dipoles will not cancel out, so there will be a net dipole moment resulting in a polar molecule. So that is the basics of molecular geometry and electron domain geometry. In the next video, part 2, we're going to talk about exceptions to the octet rule in molecular geometry and how that gives us much more interesting geometries that could fit 2 more lone pairs around our central atom even when we have 4 atoms. And we get many different shapes that have a lot of different nuances that we have to talk about. Alright, thank you. See you in the next video.